Hi everyone, this class will be an introduction to the Unix operating system, and the emphasis will be on usability, so that's why I called it the practical introduction. Hopefully after this class you'll be able to try some things on your own and enjoy the pleasure of using Unix, even if you use it just for fun. But if you have a professional use of it, even better. At worst, you'll just put it on your resume, which is not bad either. Okay, so the things we'll cover are not that many because we don't have much time. This is going to be a two-part lecture, and it will start with an overview on the operating system itself, and then we'll go into specific commands and utilities, and we'll show you how it's used and what we can do with them. And we'll go over the file system first schematically, and then we'll just do some hands-on practice with creating files, directories, etc. And we'll learn how this file system was created and what we can do with files in Unix. And the last portion will be a touch of scripting, and scripting is the art of putting together several commands and using it as sort of a program or instructions that are grouped together to do something useful. As an example, I can give you, let's say you have some maintenance type of work to do, like think of something, you need to archive some files, and you need to write some notes regarding those files and store them somewhere. So you can do that with a pre-written script, and you'll just give the parameters every time you need to do that, and the script will run and do the stuff for you. So in other words, instead of writing a bunch of commands and deciding what to do according to the outcome of those commands, this script will do it for you. It's the same as writing a program in any other language that you are familiar with. As far as books go, I recommend a book called Your Unix. I think it has it's a very good book for learning the material, and it's also a good book as a desk reference. So Unix in a nutshell is sort of a desk reference mainly, after you already know how to work with it. Doesn't have many explanations, but I think that book, Your Unix, is by far one of the best I've seen. I've seen about 20 or 25 different books. I have a few more here on the list. Those are also available online on a trial basis if you log on to this URL over here. And they cover different aspects of Unix. And if you really want to get into different things, then you need more specifics, and then you can browse one of those books. And those are additional books. In addition to just knowing Unix, there are other tools that are related, like Perl scripting language is also a tool that's being used in the Unix world, and it's closely related. Corn shell is a very common shell that we use, and we'll talk about what shell is later on. But anyway, this is a very popular sort of programming environment, I would say, without telling you too many things about shells yet. On the web, Google is using Linux, and well, Linux is one of the flavors of Unix, and they have even a specialized search engine for all the terms that you can think of in regards to Unix commands, utilities, etc. And of course, Wikipedia is always a good source of reference. Okay, those guys are the guys that basically invented the operating system, Ken Thompson and Dennis Ritchie. Dennis Ritchie also invented the C programming language, and actually Ken Thompson also had to do something with C. He invented a programming language called the B programming language, which is a precursor to C. And here those guys are receiving a Medal of Technology honor from President Clinton. I think it was 1999. And those guys also won the Turing Prize, which is like the Nobel Prize for computer scientists. So yes, we have to thank them for having the Unix operating system around. And actually, the operating system Unix came about because there was a game that those guys in Bell Labs, Ken Thompson and Dennis Ritchie, used to play, and they played it on another computer, but that computer was too expensive to maintain. It was a GE computer, and it's called the GE 645, and AT&T decided, Bell Labs was part of AT&T, and AT&T decided that it was too expensive to carry it. They gave it away, and therefore, in order to continue and play the game, it was sort of a Star Wars game. Ritchie and Thompson sat down and wrote another operating system that would work with the old PDP-7, and this is basically the birth of Unix. And before it was UNIX, it was UNICS, and that was a variation of an operating system that was called Multics at the time, and Multics was the one that was running on that GE 645 machine that was too expensive to maintain. So Unix was basically a stripped-down version of Multics. A little bit more history. The original Unix with CS was developed around 1969 and was used on the PDP-7. Then after the PDP-7 goes away, the PDP-11 was introduced, and the system was rewritten, and then version 1 of Unix with an X is considered 1971, and there were some more features that were added over the years. Version 3, actually version 3 is the first one that AT&T supported for real, and version 6 was probably one of the more stable ones, and then with version 7 it started going off to different vendors. It was licensed for universities, for some commercial usage, and well, and Unix is actually written in the C programming language. C is both a high-level and a low-level language, so you can write an operating system with this kind of language. This is another shot from those old days of Thompson and Ritchie sitting there with this huge computer, the PDP-11, and doesn't have much power comparing to today's computers, but that was then in the early 70s. Okay, over the years, Unix evolved, and here you can see the timeline. On the left you see the years, and here you can see the different editions of the operating system, and then how it started offshooting to different variations. And basically one of the problems of AT&T in commercializing Unix was that they were not free to do that because they were supervised by the government, and they needed an operating system or a computer system to handle switches for their operation, but they couldn't sell it. So that's why they started licensing it to schools and to other businesses for very low fee. Okay, here we see another development at Berkeley, and the reason it was developed further in Berkeley is because it's a very simple reason. Ken Thompson had a sabbatical in 1975-76, I think it was, in University of California at Berkeley, and he brought over this idea, and they developed another variation of Unix called BSD, Berkeley System. I don't know what the D stands for, but anyway, BSD is from Berkeley. Then later on, all the other commercial success of Unix came in the form of different names, different variations, basically on the same system, the same base or kernel. IBM called it AIX, Sun called it Solaris, it was Ultrix on Compaq, and HP UX on HP, etc. Even Microsoft called it Xenix, and then sold it to SCO, another company. Then later there was some sort of standardization of Unix. The standard is called POSIX, and POSIX is still like a standard that every Unix developer or user knows that every flavor of Unix will have the things that are standard on POSIX. And I think everything that we'll do here is basically POSIX standard. And then the biggest clones of them all, Linux, of course, written by Linus Torvalds in 1991, and it's the most popular Unix variant, and it's a free operating system, it's open source, and different places package it and add some utilities or GUI interface and sell it for a nominal fee of around $10 or $20. And the BSD and BSD Lite from Berkeley also evolved, and one of the major users of BSD is Apple with their Mac operating system, and we'll touch on that as well. So here is just a few headlines for the different variations of Unix. IBM spends a lot of money on Unix, or Linux actually, and today it's very substantial, to the point that 70% of the web servers are Unix based. So it's if you're a web developer or you aspire to be a web developer, it's definitely recommended to know the basics of Linux or Unix. So this will give you some added value, I think. Here is the stuff that Apple did. They actually abandoned their old Mac operating system in between 96 and 2000, and they bought a company called Next. The CEO of that company was Steve Jobs, and that's when Steve Jobs returned to Apple. And they took that platform and they developed their Mac OS 10 over the operating system called Darwin, which is a variation of BSD Lite, and they called the GUI that they developed Aqua. That's why you can see here the fish. Aqua is water, so the fish and the apple, and it's all based on open source. So Darwin is underneath the layers that you see on the Mac operating system. And this is one of the reasons that Mac OS is very stable and almost never crashes, because Unix is very solid, and that's basically the engine that's behind Mac OS. Why did Unix succeed? It's technically very strong, it's very robust, it was used mainly for research and not commercial, so it was improved a lot, and there weren't too many fights over it. People just added more and more things. The PDP-11 didn't have a great operating system, so Unix was good news for it. And as I said before, AT&T had some legal problems with entering the computer business, so they needed software for their switches, so the license was very inexpensive. The government told them you can't make money on other things than telephone, so that's why Unix spread out almost for free. And in addition to that, the open source movement that contributed many things on the way to the Unix operating system, of course, improved the platform. And when so many people in the world are sitting there and trying to improve each and every utility, each and every program, eventually you get a very good product. And then once this was free, a lot of vendors jumped on the bandwagon, and they included Linux together with their machines because they didn't have to pay any license fee, and it was cheaper than putting Microsoft Windows or any other server operating system that was at the time for servers. And today the Linux distributions are called different names, and they're all based more or less on the same kernel, which we'll talk about shortly. But some names that you can see out there are over here. Red Hat, Fedora is actually the version that we're using here for the demo, and Ubuntu is very popular, and you can see any of those names exist in different places, advertised on different computers. Okay, so now let's get more into the details, and some of the Unix philosophy has to do with the following. The Unix developers, or the people that dealt with it originally, they thought that small was beautiful. Do something small and easy to understand, and people will use it. Easy to maintain and efficient, etc. So what they did is they developed a set of tools. Each tool does something small, but does it very efficiently and very quickly, and it's almost unbreakable, because when you write a small piece of code, there aren't many chances of making an error. So it's mostly bug-free, and the idea was that if you need to do something more complex, you combine several of those programs, and then if each and every small part works perfectly, then your bigger thing will work as long as you put it together correctly, but that's up to you already. And another concept is make every program a filter, which means data goes into the program, data comes out of the program in sort of a standard way. So you have standard input, standard output, and then programs can run in succession, and the second program can use the first program's output as its input, and then give its output to the third program, and so on and so forth, which we'll see very shortly. So one of the elements that allows that type of functionality in Unix is something that's called the pipe symbol. Pipe symbol is that vertical line that you can find under the delete key on your keyboard. It's either under the delete key or next to the backspace, depending on what type of keyboard you have. But anyway, that pipe symbol is basically saying that run the program on the left of the pipe and use the output of that program as an input to the program that's on the right side of the pipe. So if you look at the example here, I have a program that's called who. Who is a program that displays who is logged in right now to the operating system. And then I have the pipe symbol. And then I have a utility called awk with some parameter. So without going into the details, all I'll say right now is that when who runs, it produces some output. That output goes as input into the awk program. The awk does its work, and then the output of the awk is piped into the sort program. Sort program gets the output from awk as an input. It sorts it. It's a simple sort. And then the output of sort goes and gets piped into a utility called unique, or command called unique, and that one in turn gets piped into a utility called sed, which is stream editor with some parameter, and at the end of the whole this line of code we get some output. So this is the concept of piping, and now since we have the system in front of us, let's go and do some example for piping, which will demonstrate the power of this tool. So if you can all log in, please. I think you need to use a user ID called user, and the password is simply the word password. That's what I used, at least. So if you have that, then let's go and do something simpler than what we have here. We'll create a file and we'll put some data in the file, and then we'll try to display the data and pipe it through another program and see what happens. So let's go and create let's clear the screen. Let's type the word touch. Touch creates a file for you. We'll give it a name, let's say T1, and let me just verify that it was created. Just type ls. We'll go over those commands a little bit later, but I'm just using very simple commands to create a file and see if it exists. And if you see, there is a T1 here, and actually I can use vi to edit that file. So let's do vi T1, and I will not go into the vi editor right now because it will take too much time. but let's just go into insert mode, hit I, and then type this is the first line of the first file, and then hit escape, and now colon X, hit enter, and we created a file called T1, and we had one line in that file. If we want to see that line, we can say cat, which stands for concatenate, and then the file name T1. Don't worry about the commands right now, we'll go over them one by one a little later on. But anyway, so this shows you, it basically lists a file, it has one line, and now let's try piping. So let's do cat T1 pipe symbol, and let's do oak, and then we'll use a quote sign, curly brace, left curly brace, and let's say $1, print $1, comma, dollar, how many words we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, $9, close curly brace, close quote. So you already see that what oak does, it divides what we have on the line and is separated by spaces into fields, and it calls them $1, $2, etc. So the word this is going to be mapped to $1, and the word file will be mapped to $9. And so what we're doing here is we're listing T1, and then we're piping that line, that file, which is a line, into the oak utility. The oak utility takes the line and prints only the first word and the 9th word, and what we'll see is the result of that, which will be this file. Hit enter, and indeed that's what it did. And if you want to see that it works correctly, we can change, instead of $9 to $8, and then you will see that instead of the word file, it will put the word first. So this time it will say this first. So I think now you're convinced that oak really marks those words with $1 through $9 in this case. So anyway, this was a sample of piping. So let's go back to our presentation. Okay, so continuing with the Unix philosophy, Unix avoids interfaces that are cumbersome and long, and the fact that we write on the command line and we always see what we're doing is easy to understand. So the things that Unix avoids is complex structures and massive code behind interfaces, and it's also avoiding the problem of, as I said, many bugs that exist on other operating systems that are very complicated. Another element of Unix is when your command succeeds, it basically doesn't tell you anything unless there is output to look at. Let's look at another example. If we go back to the file we created, it's out there because when we type cat T1, it gives us the file, it shows us the file. Now if we decide to remove this file and we'll do it with rm and then the file name, Unix will not tell us, will not warn us, are you sure you want to delete? It will not tell us that it's been deleted. It will just go back and show the prompt, and you can try that. Boom. And now, if we try again the cat command, by the way, with the arrows, you can, arrow up will bring you the latest command. So every time you go arrow up, you go through the commands backward. So if I go 2 commands back, cat t1, enter, will say that no such file or directory because I just removed it. And if you saw after the removal, it didn't say anything. So this is one of the elements of Unix. As we said here, silence is golden, at least for Unix. Well, if something goes wrong, as we saw just now, it told us that there is no file, there's no such file, so it does give you an indication if you have an error. But if you don't have an error, then everything is fine, it executes and doesn't report. Another element of Unix is thinking hierarchically, and many things are done in a hierarchical mode, including the file system, and we'll talk about it a little later. But this is something that's probably easy for humans to comprehend. If you start small, you start with a certain base, then you branch into several branches, then each branch branches into other several branches. It probably, in our brains, it registers easily if we can figure out how the hierarchy of things work. It's common for a lot of things in life, you know, starting from a company structure, through websites, through almost everything you can think of. You can think of the larger picture and then drill down through the details with different levels and more details as you go down the path. Some of the highlights of Unix and its traits: it's portable, it can run on different hardware, it's implemented with C, and C is a universal language that can be that almost every computer in the world has a compiler for, so it can basically be installed on many machines. We already said that the file system is hierarchical, and the file system is a good abstraction because it's also using devices. We'll see later on that it basically uses a device like a printer or a terminal as part of the file system. It designates a name that will be for the device, and that name is part of the file system. It allows multitasking, multi-users. It allows control and security. It gives us the ability to interact between processes, and a process is a program that started running, basically. For example, pipes are sort of interaction between programs, because one program does something and interacts with another program, and they don't even have to, they have to coordinate what they're doing, but the first one doesn't need to completely finish its job before the second one takes over. There are some mechanisms to tell, from one program to tell the other that, okay, I finished doing a certain amount of work, here's the buffer, take it, do whatever you want, and I will continue to do things on the rest of the data that I have. Then I'll send you the next buffer. The second program doesn't even know that it received its input from a program. It may think it received its input from a human. It really doesn't know the difference between getting the data from a program or from a person typing on a screen. So that's one of the beauties in Unix, that each process is independent, but they can still communicate because the Unix operating system is coordinating those interactions with what we call IPC, inter-process communication. Unix has a lot of different software tools. I mentioned Perl. It has many other tools that are very, very powerful, and some of the things will be evident when we do more commands and utilities. It gives us several scripting languages like the Corn shell or the Bash shell and Perl and a few other things. It allows TCP/IP networking. So going back to the big picture, an operating system is basically what governs everything on your computer. And the term kernel I mentioned a couple of times already. The kernel performs some critical system functions and interacts with the hardware. And we'll see a little bit more about the kernel, but the kernel is sort of a portion of the operating system, if you will, a small portion that's very critical and very important. And we'll see how the rest of the operating system interacts with the kernel. And then we have system utilities. Those are programs and libraries that contain commands or programs with different functions that can be used to interact with hardware through the kernel and do different things that we'll see later. So going back to the kernel is something that gets loaded when we boot the computer, and it stays in the memory of the computer, in the physical memory, not virtual. Because it's small, it can stay there, for as long as the computer is on, and it's critical that it will react fast to everything that we need, and therefore it's in memory. And it manages the CPU cycles, priorities for different jobs, different users. It manages the virtual memory for programs. It manages the file system and all the devices that are connected, the disk drives, the printers, the terminals, etc. So that's basically what the kernel does. And if you look at this picture schematically, we have at the lower level, we have the hardware devices, including the memory, the printer, disk, terminal, etc., etc. Then we have the kernel, which is directly interacting with those devices, and it attaches to the device controllers with device drivers that are small programs that allow us to control the devices. Actually, the devices are being controlled by their own controller. Each device has sort of a small brain that gets activated via the device driver, and the kernel has a way to interact and give instructions to those devices. And on the upper level, we see that's basically our domain where we interact with the operating system. You see shell scripts, C programs, compilers. System calls are things that are used from our programs or our scripts to tell the kernel that we need some sort of services. For example, we need to read a file, and we have an abstraction of a file. The kernel takes that via a system call, and it knows according to the name what address we have to pick up the file from. We may have several disks, so it knows according to the name of the file. If it can identify it, it will go to the appropriate device and will bring up the input from the file, or write to a file, or do other things. So there is this mechanism of interacting between whatever our programs need to do or our individual commands need to do and what the kernel instructs the rest of the system to do. The kernel has several subsystems. One of them is the process management, scheduling processes, how to run, how to utilize the CPU, the inter-process communication that we mentioned before. And it has memory management. It tells every program in the system that when it enters the execution mode, it virtually has the entire computer's memory to use. Even if it's not true, it manages the memory and it allocates the memory that the program needs when it needs it, and it does the swapping of programs or program pages back and forth. We'll not go into that. That's not a very simple explanation, but only if you want to really learn operating systems you can dwell on that. And another subsystem is the I/O, which interacts with devices, manages buffers, cache, etc. Another thing that the kernel uses are system calls. System calls are calls that are being made at the higher level, where we saw that 3-layer picture. The higher level, the shell script or the command, is issuing a system call, and then the kernel is taking that system call. It does what's called a trap. It changes the mode of operating to privilege mode from user mode, and it interacts with a lower level with the controllers of different devices and bring us back the result that we need as a result of that system call. Okay, that was a little bit of theory, but now we'll go more into practical stuff. So here are some commands that we can try. Try to type date, see what you get. A very popular command, ls, which I think I already used. ls shows us on the current directory, and we'll talk about current directory in a minute, shows us the files that exist. And if we want to see a longer version with more details, we can do ls -l, the option -l, and this will give us each and every file in a line, and we'll go and analyze what elements exist here on the longer version of ls a little bit later. But for now, let's just use ls, and let's try who. You'll see who's logged on to the computer, and because you're the only one on this emulation of Fedora, you will not see many users. But normally, if you're on a server system where many people can log in, you will see all the users that are logged into the system when you type that. We saw the command cat, which is a shortcut for concatenate cat file name, and well, if we do exit, we'll get out of the shell or the Unix login. So let's not do exit yet, but let's go on to the next slide. You can also remotely log into a Unix server with several different programs. You can use something that's called Secure Shell or SSH on some platforms, Mac for example, platforms that are similar to Unix, you can go to the terminal command line and type in SSH and then your account number, your account credentials, and you log in from remote or through Windows utility called PuTTY. And if you have an account somewhere, you can remotely log into that account. Emulations for the Unix environment in order for you to practice if you want to do it at home. Cygwin, I tried. I don't know the uwin, but you can probably download it and install it on your PC at home or anywhere and play around with Unix commands. Most of the stuff that we do here, or almost all the stuff we do here, should work on that emulation. This is another description of what we said before, the system call. This is more for like diehards on operating systems. If you really want to know what's happening, how the trap to the hardware is done, this gives you the sequence on from the time that the application issues a call and through the intervention of the kernel and how it switches into privilege mode in order to execute the system call, and then it goes back and reverts to user mode. And there are many system calls that exist. If you want to read a book, even that book that I mentioned has some description regarding system calls and hardware traps, but it's too much for this lecture, so let's skip over that. And this concludes the first portion of our lecture, and the second portion will be more hands-on. We'll do more things, so let's take a break now, 10 minutes break, and when we come back we'll be ready to do our hands-on exercises. Thank you for listening, and enjoy the break.